talkSTEM is a nonprofit organization that I founded 5 years ago, focused on building a community of people interested in engaging our youth in STEM learning and teaching, both in and out of school. And walkSTEM is our signature program that connects the real world to STEM. We'll be talking a little bit more about it today. So what is computational thinking? I'd love you to share any thoughts you have in the chat, but it can be, obviously, it's a broad topic and can include any number of things. And that's what the premise of today's presentation is about. Paul and I have been working together for a number of years. He's been a great partner and really shown a lot of interest in what talkSTEM is doing, and then walkSTEM once we got that initiative going. So over here, I'm just showing you, I guess we're suggesting that whether kids are building blocks, looking at artwork or creating artwork, or I got this chart from the ISTE, which is the International Society of Technology Education site. So really, we're coming at this from a very broad idea. Whether you're a teacher in a self-contained classroom in elementary school, whether you're a math teacher, a computer science teacher, an English language arts teacher, or an art teacher, we really feel that what we're going to share with you fits in all those spaces. And do, by the way, in the chat, if you have a chance, share with us what your teaching context is and who you teach. Certainly, if you have questions as you go, by the way, I will do my very best to respond. If not during this presentation, then follow up by email. So some big questions I'd love for you to keep in the back of your mind as Paul goes through his part of the presentation. He's going to get going pretty soon, talking about a particular activity that he did as part of the talkSTEM team with his students in UT Dallas. I'd like you to think about how could these types of activities really make a difference when we consider equity in STEM education, equity even in the workforce. This webinar is targeting grades 3 through 8 teachers, but frankly, I mean, it can be extended to all grade levels. Why should we even care whether or not kids see themselves as computational thinkers? Think about that. How would your students respond to the ideas that they already do computational thinking every day, from the minute they wake up to the time they go to bed, more or less, and that this is the same thinking used to create some of their favorite apps, games, and more? Paul, I'm going to hand it over to you.
Okay, Koshi, thank you. Something I think that's common to both the arts and sciences is that we start to question things. So when we look around at nature or things that we've created, like automobiles and so on, I think the first step is sitting down or standing up and looking at something and focusing on that thing and spending some time attending to it. Next slide. So that's kind of the first step for some of the things I'll be talking about is, this is a picture of a live oak tree. It's an oak tree that I'm familiar with because I lived in Florida for many years, and we had these sprawling oak trees everywhere, and I think they're in Texas as well. But if you go out and you look at it carefully, maybe spending 1 minute, 2 minutes, 5 minutes, the idea is to stare at it, to focus on it, and to attend to it. Next slide. So I think a first good step of computational thinking is, first of all, take the thing you're looking at, maybe the live oak tree or a tree in your yard or a tree near the school, and start to analyze it. In this particular case, we know that trees have trunks and they have a root system which we can see some of, or in many cases you can't see it at all. Depends on the kind of tree. But then there's branches, there's twigs, and eventually you've got leaves and fruit. I was talking with Koshi yesterday, and we were saying, you know, this is a bit like anatomy, right? You're looking at the tree anatomically. What are its parts? What are its constituents? Next slide. Okay, now the next step is, once we know the parts of the tree, once we see the tree and we identify, right, its parts, then you want to link them together. Now, some of you may be familiar with this. It's called a concept map. And to create a concept map, you just take those components or parts, or indeed just any concept, and you link it with another concept using a straight line. So for example, trees have parts, and you can see the tree in the middle, and you can see parts, and the parts are branches, leaves, roots, and trunk. And so I just want to note, this is also very connected to English and the study of the language arts. Because in language arts, sometimes we diagram sentences. Well, this is quite similar actually to diagramming sentences. You're diagramming the meaning of the sentence rather than the vocabulary or the syntax. And so these are very useful in computer science, and computer scientists use this kind of organization every day. But as Koshi mentioned, we can experience it ourselves without necessarily coding. Next slide. So a question might be too that when you look at a tree outside, you go to the tree and you go, how would I make this? Now, this is the same question that Walt Disney Studios asks and Pixar films, because in Lord of the Rings and all of those great movies that we go out and see, or I guess nowadays we look at our television sets, but you know, everything in those, all the computer graphics, all the so-called CG has to use models and methods for describing how to make a tree. How to make a tree so that it looks like one, so the viewer is convinced, yeah, it looks like a tree. So the goal here is to talk about how, not what. And this is the biological analogy here is physiology. So anatomy is the parts of the tree. Physiology would be the behavior, which can be how to make it. Okay, next slide. Oops, looks like we missed a slide, or did we go too far? Yeah, so this is just an example. Trees are so popular in our culture, in our lives, in our history as human beings that we've taken them as analogies to other things. So you've all seen a family tree where you're at the bottom, right? And then you've got your parents on either side. And so this is a concept map as well. So when we talked about concept maps, think of this as a concept map, but it's organizing the information about family into a tree. So thinking about a tree as a kind of concept map is fine. You'll notice it's a little different because it's got this hierarchical kind of structure, this top-down or bottom-up structure, which the concept map we looked at before had more of a network structure. Okay, next slide. So indeed, you know, one of the things I love talking to people about, including all of you, is that the abstractions that a computer scientist uses every day are literally everywhere. They're inside the house, they're outside the house. Everywhere you look, it's the trick is some lesson plans, some ideas on how you do this. How do you go about seeing computing everywhere? So computing and computer scientists, that's my primary title and what I do. And, you know, we organize our knowledge in certain ways, like the concept map of the tree. our field is an extension of mathematics. So for all those math educators out there, there's really great opportunities to connect what you're doing in mathematics to this entire talk, because there's an area in math called discrete math, which frequently is not taught in K to 12, but that's the that's the Bible, that's the basis of computer science. So when computer scientists enter college, or budding computer scientists, they take discrete math. Next, to look further, they study data structures and networks, much like we talked about with the concept map. And the concept map in the family tree were networks and trees. And so we tend to, getting back to the tree, we use it as a kind of analogy, as an abstraction, like we did with the family tree. I mean, the family tree isn't a natural tree, right? You don't see a family tree when you go outside, but you can think of the tree as like an abstraction of not just trees, not just natural trees, but family trees and just about everything else.